Ladies and gentlemen, good morning everyone. First, I'm a PhD student in materials chemistry at Biskra University, and it is a good pleasure and honor for being a part in the first international conference on chemical matters and environment preservation to represent my research, which is titled Zinc Doping Effect on Electrochemical Performance of Lanthanum Cobaltate Perovskite as Electrode Materials for High-Performance Supercapacitors. So, our work or study can be summarized as follows: Introduction, experimental section, results and discussion, and we will finish by conclusion. So what I have here is a quick slide overviewing some types of energy storage devices such as conventional capacitors, supercapacitors, batteries, and the fuel cells. Among these energy storage systems, supercapacitors attracting a great attention recently due to their high power density, moderate energy density, fast charging discharging rate, and superior long cycle lifetime. Furthermore, electrodes materials have a significant impact on the performance of supercapacitors. Substantial efforts have been devoted to explore efficient and scalable electrode materials for supercapacitors. So it was fun to think about where things are at today, and I made this plot for energy storage. As you can see, on y-axis we have stability, so this is the number we can recharge supercapacitors, and x-axis we have specific capacity. It is almost always. As we increase the specific capacity, the stability or the rechargeability of the system falls. So, how we do increase the specific capacity but will maintain excellent stability? This is the battle that we try to find. So you see that in the y-axis, this is really concerned with efficiency, scalability, and cost of energy storage system. So exploring efficient and scalable electrode materials that exhibit high specific capacity and long cycle life is the key challenge here. Experimental section. The Sol-Gel technique was used to prepare a series of zinc-doped lanthanum cobaltate perovskite. First, metals nitrates were dissolved in ethanol separately, while the citric acid was added dropwise to the mixture solution, under magnetic steering at about 80 degrees Celsius, until the formation of a gel. Afterward, the as-prepared gel was dried at 100 degrees Celsius for 24 hours, and then the obtained dry gel was ground by a mortar and then calcined at 1100 degrees Celsius in air for 6 hours with a heating rate of 5 degrees per minute to provide a black powder of zinc-doped lanthanum cobaltate perovskite, and then characterized by several techniques such as X-ray diffraction, Fourier transform infrared spectroscopy, scanning electron microscopy, and electrochemical measurements. To fabricate the working electrodes for the electrochemical measurements, a sheet of nickel foam was cleaned in ethanol bisonication for 2 hours and then dried at 100 degrees Celsius for an hour. On the other hand, the solid precursor of lanthanum cobaltate doped with zinc as activate material, PVDF as a binder, and the black carbon as a conductive agent were mixed in a weight ratio of 80-10-10%. Thereafter sonicated in NMP solvent for 24 hours to form homogeneous slurry. Afterward, the obtained slurry was coated by a doctor blade method onto the pretreated nickel foam and dried at 80 degrees Celsius for 24 hours. Results and discussion. Figure 3 displays the X-ray diffraction patterns of lanthanum cobaltate doped with zinc after calcination at 1100 degrees Celsius. It clearly shows that all the patterns are rather similar, and they exhibit a pure hexagonal perovskite structure of lanthanum cobaltate. Also, a slight shift of peaks to the lower 2 theta value with the increasing of zinc amount. That can be attributed to the substitution of cobalt ions by zinc ions. Figure 4 shows the infrared spectra of zinc-doped lanthanum cobaltate calcined at 1100 degrees Celsius. All these spectra are rather similar. The infrared band found at about 418 cm-1 can be attributed to lanthanum oxygen stretching vibration. The doublet absorption bands appeared at about 561 and 595 cm-1 can be assigned to oxygen-metal-oxygen banding and metal-oxygen stretching vibration of octahedral coordinate MO6 respectively. These results reconfirm the formation of perovskite strata and support the XRD results above. Figure 5 depicts some images of LCZ calcined at 1100 degrees Celsius. The micrographs images indicate that grain with different shapes and size are formed with very well pronounced agglomeration. Moreover, it clearly shows that LCZ05 has the smallest grain size and the porous morphology. Electrochemical measurements. Figure 6 displays cyclic voltammograms of LCZ electrodes recorded at scan rate of 10 mV per second in 1 molar potassium hydroxide. The obtained CV curves have a similar form and clearly reveal the existence of redox peaks indicating that LCZ electrodes have a battery-type behavior. On the other hand, the antigrade area of the CV curves indicate that LCZ05 possesses the highest specific capacity compared with the other composition. Figure 7 shows the galvanostatic charge-discharge curves of LCZ electrodes recorded at a current density of 1 amps per gram. The obtained GCD curve revealed a battery-type profile. The charge-discharge curves exhibited a potential plateau which confirmed the presence of a Faradaic oxidoreduction reaction. This result matching well with the result found in cyclic voltammetry. Figure 8 illustrates the electrochemical impedance spectrum of LCZ electrode recorded at open circuit potential. All curves exhibit the presence of a semicircle. The value of impedance parameters was calculated using NOVA software on the basis of the equivalent circuit, in which LCZ05 shows the low value of charge transfer resistance, solution resistance, and the highest double layer capacity, indicating that LCZ05 has excellent electrochemical activity, easy accessibility for electrolyte ions on the electrode surface, and much more electrochemical active surface area, respectively. Figure 9 shows the cycling performance of LCZ05 electrode at a constant current density. After 5,000 charge discharging cycle, capacity retention was approximately 82% of initial capacity, with a Coulombic efficiency of 98%, indicating the good stability and reversibility of LCZ05 electrode. Conclusion: zinc-doped lanthanum cobaltate perovskite were successfully prepared using the sol-gel method. X-ray diffraction and infrared analysis enabled us to show the presence of the pure perovskite structure. Scanning electron microscopy shows that different shapes and sizes of particles are formed with a very well pronounced agglomeration. The electrochemical studies indicated that LCZ, 0.05 electrode has the highest specific capacity with a good stability. Thank you for your attention.